And now we're going to solve a real engineering problem. So we're going to really use scale analysis to essentially solve flow over a plate. So what's happening is the fluid's coming in, flowing over a solid plate. It's coming in at some U infinity, P infinity, or U infinity, P naught, whichever you prefer. Environmental, pressure, and some, steady velocity, U infinity. It's steady flow over the plate, so steady. And so, this would be an airplane wing, top of a wing, bottom of a wing, flowing through the air. So what's really going to happen? Well, it turns out there's something, we're going to define something called delta. This delta here is the viscous boundary layer. So this is the viscous boundary layer. And that's where the viscosity effects have affected the flow. So beyond delta, the flow is still U infinity, P infinity. Nothing's happened. This flow up here doesn't even know there's a wall. There's been no effect from the wall on this flow. As the flow comes by, of course, it has the no-slip condition. So the velocity of the fluid goes to zero when it hits the wall, and the viscous effects start to impinge into the flow as layer upon layer of fluid feels the effect of that slower moving fluid dragging it back as it tries to go past the wall. And that viscous boundary layer is going to grow as those viscous effects have time to get into the flow. So that's just true. But we're going to show that. We're going to actually calculate how big is this viscous boundary layer as a function of velocity and pressure and these other factors. We can show that using our scale analysis techniques and these equations, these very difficult partial differential equations. So we have the x momentum equation and the y momentum equation. We only have two dimensions in this flow. Imagine it's going in and out of the paper just uniformly. So we have x going in the plate length direction and y is going to be straight up. And here are two equations. Well, we said it's steady flow, so of course that's immediately going to wipe out, that's supposed to be a t anyway, going to wipe out those two terms. So we have du dt, dv dt is equal to 0. And we have, the inertial terms, the pressure terms, and the viscous terms still in there in the game. We're going to also use mass conservation. So we'll write that one down as well. Mass conservation, which we said, and you have shown, is du dx plus dv dy is equal to 0. So that's all it is in two dimensions. We're now going to make an assumption, and it'll prove to be a correct assumption, but it allows us to move forward, and then we can verify it. We're going to assume that the viscous boundary layer is small. And what we mean by that is that L is much, much greater than delta. So obviously this assumption will not apply right here at the tip of the plate where L, is if L were very small, then delta and L would be similar sizes. But if you have a nice long plate here and delta is going to stay close to this, we think, so we're going to assume initially that L is much, much bigger than delta. And that's going to allow us to figure out which of these terms is significant and which of these terms is not significant and allow us to make some progress on this problem. All right, so we already showed how to do this in the last lecture, but we're going to take this equation here. Notice we have no V scale again. We need a scale for V. So we have that the scale for U, well, it goes from U infinity to 0 because the wall is there's no slip condition. So we've got U infinity, I'm going to say du dx here is of order U infinity minus 0. That's the range that the U velocity takes. And then I've got du dx, and the scale for x is L. So that's my order for that. For dv dy, what do I have there? Well, I have for V scale, I just have V, and I don't know what it is. It also goes to 0 because there's a wall, and also there's 0 velocity out here in this part of the flow in V direction. There's no Y velocity out here. And my Y scale now is delta. So that's the obstruction in the Y direction that's going to change the flow. So that's my Y scale. So those are my two terms, and then I can plug these into the mass conservation to get a scale for V. So I go ahead just like I did last time in the last lecture. So I have U infinity over L has got to be of order V over delta because these two things have to be the same size or they can't add together and end up being 0. If this is 1 and this is negative 100, that won't add to 0. If this is a million and this is, 0.1, you can't add them and get to 0. The only way you can add two things and get them to be 0 is if they are basically the same size, so that you can make one of them negative and they'll come out to 0. So I use those two things. I say, well, that means the size of this has to be the same as the size of that. Therefore, V has to be the size of delta over L times U infinity. So that's an important result right there. That's our V velocity. We have a sense for now for how big V is, if only we knew delta. Of course, we don't know delta. That's what we're seeking to find, but that's what we're going to try to do. We're now going to use that to create scales for everything. So we have all these terms, and we're going to go ahead and do this for every single term. So it's going to be very, very it's actually pretty simple. It's just kind of long. So we have a scale for V, we have a scale for U, so we can just plug all these in. So U du dx, so that's my first term, this U du dx, which is right here. I'll just do it right below this one. So that's U du dx, that's going to be U infinity for U, and U infinity for U, and x length is L, dx, so it's U infinity, and L. Then I'm going to put a comma. I don't use plus because you can't really use plus when doing scale analysis. If this is like 3 plus 4, that's 7. That's not what we're talking about. We're saying this is about this big. If this is the same size or a different size, that's all we can say. We can't say they add together. We just have to say, well, these are things that are about different sizes on this side of the equation. So on this left-hand side, we have V, which we said the V scale, we figured it out. It's delta over L U infinity. So it's delta over L U infinity. That's my V scale. So that's for this term right here. And then I have the U again, so I have U infinity again, and then I have this time Y. So that's delta. All right, so that's the left-hand side of the equation. All of that has to be of order 1 over rho. P scale I don't have. I'm just going to put P in there for now, and then L. And then I have a comma. And then I have these two viscosity terms. So I have nu, and I have the U scale for d squared U dx squared. Now it's important, here's another place people screw up. This is not U squared, it's d squared. So you could write it like this, it makes it a little clearer. D by dx of U. That's what d squared is. So there are two x terms, but there's only one u term in that term. Everybody see that? So we're going to have not u squared, we're just going to have u infinity. So I'll have to take this one and bring it down. It's u infinity, put the nu in it, divided by L and L, right? And then the second term, this guy, same thing. It's not u squared, it's just u infinity in the numerator. I have the nu out in front. And then the two of those delta squareds. All right, those are my terms. Is there anything I could do to clean this up? Well, yes. Look at this one. This is going to cancel. So on the left-hand side, I have u infinity squared over L, comma, u infinity squared over L. That is, they are the same size. So I don't need to keep both of them around. I can just say, well, I know how big these terms are. They're this size. I have 1 over rho, P over L. Notice I also dropped the minus sign because I just don't care about it. I'm not adding or subtracting anything. I'm just looking to ask how big things are. Doesn't matter if they're plus or minus to me. And finally, I've got these two terms, both multiplied by nu. I've got nu u infinity over L squared, and I've got nu u infinity over delta squared. All right, now, these two things are the same size, so we don't need them both. We're like, that's how big that left-hand stuff is. It's right there, just one of them. We keep the 1 over rho P over L for now because we don't have a choice. These two are very different sizes. They look very similar. You've got nu u infinity divided by L squared and nu u infinity divided by delta squared. But delta is much, much smaller than L, which means that this term is going to be much, much bigger than this term. This is much bigger because delta is much smaller and it's squared. So that makes a huge difference on this term. This term is going to be enormous compared to this other term. When you have an enormous number plus a very small number, you can ignore the small number. That makes the small number insignificant. So this term doesn't matter, because it's so much smaller than this term, and they're the same side of the equation. They're trying to they're added together actually up here. So we know that this is going to completely dominate that. So I can just ignore this term. It's insignificant. This one is going to be insignificant relative to that one. So I have nu u infinity over delta squared. So those are my terms that have survived so far. The final thing I'm going to be able to do is we're going to take now, so that's my x momentum equation, sorry. So that's x momentum. That's what we get from x momentum. And then to end this lecture, which is already getting long, we'll take a quick look at the y momentum scales. You know what? Let's not do that. I'll put it in a different lecture.